This video is divided into two parts. Their times are listed in the video description and in the top comment section below. The first part is on predicting binary acid and oxyacid strengths, and the second part is on why these strength differences exist, and this is an explanation of why these strength differences exist on a molecular level. So binary acids are acids that are composed of two elements because it's binary, bi, which stands for two. So here's some examples. There's hydrofluoric acid, hydrobromic acid, hydrochloric acid, and each of those are composed of two elements. There's the H, which comes off the acid, and the F, which is the more electronegative element that attracts the H. And each of these acids are composed of two, hence they are binary acids. In order to compare the strengths of these binary acids, we have to compare the elements that are not the hydrogens, because the hydrogens always remain the same. Here we have a hydrogen, here we have a hydrogen, here and here and here we have hydrogens. So the hydrogens stay the same and they don't really change their strength. What actually changes the strength is the other element that changes from acid to acid and distinguishes each different type of acid. And that element will be the decider in the acid strength. So for the binary acids, they increase in strength when the non-hydrogen element is more to the right in the periodic table. So they increase in strength as these elements progress across the period to the right. And they also increase in strength as these elements progress downwards, down the group, down the column. So in this case, H2S, the S is right here. And in HCl, the Cl is right here. And since the Cl is more to the right of S, it's to the right of S, it's more across this period, it has a higher strength, HCl, than H2S. And in this case, since the I is downwards to the Br, bromine, therefore the Hi is higher in strength than the HBr, because the acid strength increases down the group. And the HBr is higher in strength than HCl, because the Br is lower than Cl in this group. Now you might also be asking why I said that H2S is a binary acid. After all, it has 3 atoms. Well, that's because it has 2 types of elements, and therefore we consider it a binary acid. However, I would like to point out that the effect of this increase in strength across the period is stronger than the effect of the increase in strength down the group. So, for example, if we were to compare H2S, so the sulfur right here corresponds to H2S right here, and the HF, so this fluorine right here, corresponds to HF right here, which would be stronger? Well, the way we see if it's stronger or not, we see that if the F is more across from the S, we know that the HF that corresponds to this F is stronger. At the same time, though, we see that the S is below the F. So is the S stronger or the F stronger? Because if it's below the S, it technically should be stronger than the F. And if the F is across from S, the F should be stronger than the S. So it's like this across increase in strength is competing with this downwards increase in strength. Which is stronger, HF or H2S? Well, because I mentioned that the increase in strength across has a stronger effect, the HF is stronger than the H2S. Therefore, we can write that the HF has a greater magnitude of strength than the H2S. And let's say that we have H2SE right here and HF. Again, HF is more across than H2SE, but at the same time H2SE is way below the HF. So which is stronger? Is it the effect going downwards or the effect going across? Well, in this case, again, the effect going across is still stronger because it's a stronger effect than the effect going downwards. So HF is a stronger acid than H2SE. Now let's say we go way downwards, like to H2TE. So H2TE, this acid, and HF on top right here. Is the effect across or the effect downwards stronger? Well, in this case, the effect downwards, because we're so much downwards than HF, the effect downwards at this point starts to outweigh the increase in strength across. Therefore, the H2TE is stronger than the HF. But that's only when we go way down. So for the most part, this across effect is stronger than the increase in strength downwards. So let's say we compare H2SE and HCl. HCl is stronger because the effect across is stronger than the effect downwards. Unless we get like way below, but I don't think even that these elements could really form acids. These are newly discovered elements right here. Now let's move on to the oxyacids. So an oxyacid is an acid that has an H. So in both cases, here are examples with H, and these are both oxyacids. It has oxygens, so because it's an oxyacid, so oxygens, and it has another element like chlorine, bromine. Usually it's a halogen, but in some cases it's not. But it's usually three types of elements. It's hydrogen, oxygen, and another type of element. Now for the oxyacids, there are two factors that affect the strength of an oxyacid. So first is the number of oxygens. The greater number of oxygens in this oxyacid, the stronger the acid. So for example, HClO3 has a greater number of oxygens than HClO, 1 to 3. Therefore, HClO3 is a stronger acid than HClO. And the same follows for HClO4, which is much stronger than HClO and stronger than HClO3. So the higher number of oxygens, the stronger the oxyacid. The second trend is that the more electronegative this central atom is, the stronger the oxyacid. So a central atom in, let's say, these oxyacids is the atom that is not the hydrogen and not the oxygen, and it is in the center. So the bromine in this case and the chlorine in this case are the central atoms. So because the chlorine here is more electronegative than the bromine, the HClO oxyacid is stronger than the HBRO. So the more electronegative the central atom is, the stronger the oxyacid. And you can see why the chlorine is more electronegative than the bromine, is because the chlorine is above the bromine in the periodic table, and we know that on the electronegativity trend, the higher the element in the periodic table, the more electronegative it becomes. So because Cl is higher than Br, Cl is more electronegative. So which effect is stronger, the number of oxygens or the electronegativity? Well, it turns out the number of oxygens has a greater effect on the oxyacid strength than the electronegativity. So for example, in this case, we can see that the Br is less electronegative than the Cl, the central atom. So, like in this example, we know that because the Cl is more electronegative, the HClO should be technically stronger than the one with the bromine, because the Cl is more electronegative than the bromine. But because this acid, the HBrO2, contains more oxygens, it is stronger than the HClO, because the number of oxygens, the effect of the number of oxygens outweighs the effect of the electronegativity of the central atom. Part 2. Why are there such differences in acid strength? Here I'll give a molecular and more chemical explanation of why we have these differences. So you might be asking why we have an increase in strength as we go across the periodic table and an increase in strength as we go down the periodic table for binary acids. Well, here's an explanation. As we go across the periodic table, we know from our periodic trends that the electronegativity of elements increases as we go to the right. And because of this increase, we see that, for example, we have H2S and HCl, and HCl is more to the right than H2S. The Cl in this HCl is more to the right than the S in H2S. Therefore, the Cl is more electronegative than the S, because the Cl is here and the S is here. And that means that the electronegativity difference for HCl, the Cl minus the H electronegativity, is greater than the electronegativity difference for H2S, because the Cl has a greater electronegativity than the S. And because this molecule, the HCl molecule, has a greater difference in electronegativity than the H2S, simply because the Cl is more electronegative because it is more to the right, therefore the HCl is more polar than the H2S. And because the HCl is more polar, the water molecules attract more strongly to this more polar molecule than to this less polar molecule, because water is polar itself. And since water attracts better to HCl, it can rip off these H's much better, and therefore the HCl dissociates in water much more than H2S, making HCl the stronger acid. Now you might be asking, well, if we go downwards, shouldn't the acid strength decrease, not increase? Because technically we know that when we go downwards, the electronegativity of elements decreases. For example, I is less electronegative than F. It's less electronegative than F. And because of that, we should expect then that HI is a weaker acid than HF, because there's a lower difference in the electronegativity, a lower polarity, and therefore a weaker acid strength. That's what we should expect. But clearly, here it states that the acid strength increases downwards. Now, why is that? It's because the difference in electronegativity downwards is not the strongest effect contributing to the change in the strength of the acid. Instead, the increase in the atomic radius as we go downwards has a much stronger effect on acid strength than the decrease in electronegativity. So we don't care about the electronegativity as we go downwards. Instead, we care about the increasing atomic radius, and that determines our binary acid strength as we go downwards. So for example, the HF, the F is on top, and we know that the top atoms here have a lower atomic radius than the atoms towards the bottom, because each time we go downwards we add an extra shell to these atoms and their radii increase. So the F has a lower atomic radius than the I, which is lower than the F. And because of this lower atomic radius on the top, the H and the F are much closer to each other than, let's say, this HI, which are more spread out, because the atomic radius for F is lower than that of I. And because of this, the HF bonds this H more tightly because they're closer than the I bonds the H. So this bond right here is much stronger than this bond, because these atoms are much closer to each other than these atoms. And because this bond is much stronger right here, the HF acid has a much more difficult time giving out the H's than the HI. Since the HI has a weaker bond, these H's come off more easily than the H's from the HF. And because the bond strength is weaker in the HI, and because the HI gives off these H's easier due to the weaker bond strength, the acid strength for HI is higher than that for HF, because it is lower in the periodic group. And this increase in radius offsets the effects of electronegativity. Technically, if we were looking at these acids across, and we were looking at these acids downwards the same way as we were looking at the acids across, we would compare them via the electronegativity. And because F is more electronegative, we would expect the HF to be a stronger acid than the HI. But remember, the increase in radius offsets the effect of the increase in electronegativity. Therefore, we don't care about the electronegativity differences as we go downwards. Instead, the increase in radius has a stronger effect, and therefore the HI is a stronger acid than the HF. And that is why we have these trends for our binary acid. So let's see why we have these differences in strength amongst the oxyacids. We know that the first difference is that as the number of oxygen atoms increases, the strength of the oxyacid also increases. We know, for example, that HClO4, because it has more oxygens, is much stronger than HClO, which does not have as many oxygens. And why does that happen? Well, in order to see why that happens, we have to look at the structure of each of these acids. And you can see that I drew out the Lewis dot structure of the HClO. This is how it's drawn, and for the HClO4. Now, a lot of people make the mistake that they think that because the H is drawn next to the Cl, that means that the H in HClO is bonded to the Cl. In reality, it is actually bonded to the oxygen. Same story applies to HClO4. Many people believe that this means that the H is bonded to the Cl. In reality, it's actually bonded to the oxygen, one of the oxygens out of these four. So you can see the hydrogen here is bonded to one of these four oxygens. And you can see that the hydrogen's bonded to this oxygen. Now, again, why does this increase in number of oxygens increase the strength of the acid? Well, we know that oxygen is a highly electronegative element. That means it tends to really pull electrons towards itself. So we can see here I drew this like electron cloud, because remember these electrons move really fast, it almost looks like a cloud of them. I drew this electron cloud, and it's more towards the oxygen than towards the hydrogen here. You can see it's more gathered up above the oxygen, which is more electronegative than this hydrogen. And in this case, because we have more oxygens, yes, HClO4 has more oxygens than HClO. This electron cloud is more distributed across these oxygens, because each of these oxygens is highly electronegative, and if we add more of them, the electrons tend to move towards them more. So this electron cloud, instead of being around this oxygen primarily, it becomes more distributed amongst these oxygens. And what does that do? We know that the electrons are the primary reason we have bonds, because both of these elements attract towards these electrons. In the center we have the bond. So if we have less electrons in this bond right here, the bond becomes weaker. So right here we can see we have much more electrons towards the hydrogen than, let's say, here, because these electrons are more, they move more towards these more electronegative oxygens. We shift the electron density even more further away from this hydrogen because of the increased number of oxygens, and because they are electronegative, they tend to attract these electrons. And because of that, there are less electrons that tend to participate in this bond between the H and the O than, let's say, here. And because of that, this bond becomes weaker, because there are less electrons participating in it than, let's say, here. And the weaker the bond means the easier the time this acid has in giving off this hydrogen, because it attracts it less because of the weaker bond. And because of that, this acid is much stronger than this acid, because the H has come off easier. Now let's see why the second trend is also valid. We know that the second trend for our oxyacids is that as the electronegativity of the central atom increases, the acid strength also increases. So in this case, the central atom is bromine, in this case it's chlorine. Now why do we call them central atoms, even though they're not in the center? You can see the Lewis structures, is because as we have more oxygens, they are in the center. So you can see that's why it's called a central atom. But anyways, so why does the electronegativity increase of the central atom increase the acidity? And we can confirm that the electronegativity increases because the Cl is above bromine, and we know that electronegativity increases as we go up. Therefore, the Cl attracts electrons more towards itself than the bromine, and this acid strength increases. Well, this is because let's look at the structure of the acids again. Here I drew the Lewis structures for these oxyacids, and remember, the H is not bonded to this atom right here, it's bonded to the oxygen. So in this case, I drew them again. As this electronegativity of this central atom right here increases, of this atom, the electrons are more shifted towards this central atom. However, there is a difference between, let's say, an increase in the number of oxygens and an increase in the electronegativity of the central atom. And here's the difference. The effect of the increase of electronegativity of this atom is not as great as the effect of adding additional oxygens. Because here, yes, we did increase the electronegativity of this atom, but that's not even close to, like, say, adding a bunch of extra strongly electronegative elements. For example, if we had 2 bromines, yes, the effect would be huge, but here it's only, we're just changing the type. We're not adding a whole new number of them. So the effect here is much more slight than, let's say, here, where the electron density literally distributes itself, and here it doesn't do that as much. What actually happens here is that because of this increase in electronegativity that this atom has, the electron cloud begins to shift more towards this more electronegative atom, but doesn't shift so much as here. I'll draw you a diagram right now to show you what actually happens. So here is our electron cloud, and as you can see, the electron cloud shifts more towards the right when we added the Cl, because the Cl is more electronegative than bromine. But this shift is not as profound as the shift right here, which is much more drastic. You can see that there are not so many electrons left in this bond than, let's say, here. In this case, there's still a decent amount of electrons left. But this shift in electrons towards the chlorine does make the entire molecule more polar. And because the molecule becomes more polar, with an increasing electronegative central atom, the Cl in this case, this more polar molecule has an easier time forming attractions with water molecules, and because of that, the water molecules have an easier time taking off these H's, and because of that, this acid is much stronger. It's stronger than this acid, because the H's have an easier time coming off because the waters rip them off easier, because this molecule is more polar than this molecule, but is slightly for a different reason stronger than in this case, because in this case the effects are much more profound than in this case. You can see that here we added simply more strongly electronegative molecules, and here we only increase the electronegativity of one molecule. So the effect here is not as strong as, let's say, here, but it's still strong enough to make the acid stronger, because the polarity of the acid increases and it becomes more polar, and therefore the waters have an easier time ripping off these H's. So you might be also asking, well, here we see that the oxyacid with the Cl is stronger than the oxyacid with the Br, but at the same time we know that for our binary acids the trend is the opposite. So our HBr is stronger than HCl because our bromine is below Cl and therefore has a weaker bond strength to the H because it is less electronegative and because it has a much larger radius. So why is, in this case, why does the radius matter? And in this case, why does only the electronegativity matter? Why, for example, shouldn't why shouldn't the Br in this case be stronger than the Cl? Because Br does have a larger radius than Cl, and technically that would indicate a weaker bond strength and the H would come off easier. Well, the answer to the question is that, again, we need to look at the structure, and we see that in the structure for the oxyacid, the Br, the bromine, is not directly bonded to the H, and the Cl is also not directly bonded to the H. And that means that the bond strength between the H and Br doesn't matter here as much as it does in our binary acid. Instead, because of this distance that's created by this in-between O atom, only the polarity matters, the change in polarity, because the effects of the bond strength between Br and H are not so strong because obviously they're not bonded directly to each other. Instead, Br can only, in this Cl can only influence the polarity of this molecule and not really the bond strength between H and O, because it is not directly bonded. So in this case we care about electronegativity, and in this case for our binary acids, when we go down the group, we care about the bond strength because they're directly bonded. In this case, since they're not directly bonded, we don't care so much about bond strength and mostly about polarity. And that concludes our video on binary acid and oxyacid strengths.